the course on error control coding and introduction to convolutional codes. Today we are going to discuss how to decode convolutional code, and in this regard we are going to talk about a maximum likelihood decoding algorithm known as Viterbi algorithm for decoding of convolutional codes. So, we are going to illustrate Viterbi decoding of a rate 1 by n convolutional code whose memory order is m, and we are going to illustrate this decoding using a simple example of rate 1 by 2 convolutional code whose memory order is 2. In other words, it has 4 states, and we are going to assume that our transmission medium channel is a binary symmetric channel. So, as we know, a convolutional code can be represented by its corresponding state diagram or trellis diagram, and we are going to make use of the trellis representation of a convolutional code to decode it. So, initially the convolutional code is assumed to be in all 0 state. So, for time L, which is less than the memory order, we notice that the information bits are getting shifted into the encoder 1 bit at a time, and the number of states get doubled. So, initially it is in all 0 state, then once 1 bit get in, there are 2 possibilities where we can be in, and so as long as L is less than memory order, we see at each time instance the number of possibilities of number of states gets doubled until we reach time L equal to m, when we reach all possible states, which is basically 2 raised to power m, because our convolutional code has a memory of m. So, total it has 2 raised to power m states. So, since we are considering a rate 1 by n code, so k is 1. So, each time instance we have one information bit that enters the encoder at each time. So, there are 2 possible branches leaving each state, one corresponding to information bit 0, other corresponding to information bit 1. So, in our trellis diagram we will see that there are 2 branches leaving each state. Now, what happens when the time instance is more than the memory order? We will see that 2 branches are merging into each state, and encoding of information sequence can be considered as if we are tracing a path through this trellis. So, any path through this trellis is a valid code word. This is just an example of a trellis of a convolutional code. So, initially, as I said, we start off with all 0 state. So, initially the encoder is assumed to be in all 0 state. So, until say in this particular example the number of states is 4. You can see 0 0, 0 1, 1 0, 1 1. These are the 4 states. I am denoting them by 0 0, 0 1, 1 0 and 1 1. So, until you reach time t equal to 2, which is the memory order of this code, we will see that number of states are getting doubled. Initially there was only 1 state, all 0 state, then you had 2 states, and then you had 4 states. And you can see from each state there are 2 branches leaving that particular state. And once your time becomes more than m, then we see that at each state there are 2 branches which are merging. Okay. I am just denoting, so this is on the x axis is my time, I am just denoting them by level, first level, second level, third level, fourth level, which is just how the time is progressing. Now, usually after we encode the information sequence, we terminate the convolutional code. And what do we mean by terminate the convolutional code? We bring the convolutional code back into all 0 state. So, the encoder is typically returned to all 0 state after we have encoded our L bit sequence. So, if you have an information sequence which is L bit denoted by U, so our information sequence is U0, U1, U2, UL minus 1, where these are basically zeros and ones. Now, during the termination process, because we are trying to bring it back to all 0 state, what happens is number of states get reduced by half until all the trellis path will converge to all 0 state. So, as we said, for time less than memory order, there is only one path of length L entering each state, each node. You can see, go back to this diagram, up to this path, there is only one. Let us say I want to reach 1 1 from 0 0, there is only one path through this. I want to reach here, there is only one path. I want to reach this state, there is only one path. Want to reach this state, there is only one path. So, until time is less than equal to memory order, there is exactly one path of length L entering each node at each time. And for L greater than m, there are 2 raised to power L minus m paths of length L entering each state at each time instance. And total there are 2 raised to power L paths of length L in this trellis diagram. So, let us consider how we are going to decode this convolutional code, which can be represented by its trellis diagram. So, we are considering a binary symmetric channel. Now, recall what is a binary symmetric channel. So, we have 2 inputs, zeros and 1. Similarly, we have 2 output, 0 and 1. So, there is a 1 minus p probability of getting the bits correctly, and then there is a crossover probability p of bits getting flipped. So, this is our binary symmetric channel. So, let us consider that we have an information sequence of length L denoted by U, and it has been encoded into a sequence coded length n, which is coded using a RAID 1 by n code. Now, L corresponds to number of information bits. Now, remember, we are terminating the convolutional encoders. So, we require m number of bits to terminate it, to bring it back to all 0 state. So, total basically number of bits including the tail bits or termination bits will be L plus m, and since it is a RAID 1 by n code, the code sequence length will be given by L plus m into n. So, our code sequence is of length L plus m, denoted by V0, V1, V2, V L plus m minus n, and where each of them V0, V1, V2, VL are basically n bits. So, if you transmit this code sequence over this binary symmetric channel, what we receive is denoted by, receive sequence is denoted by R. So, we receive R0, R1, R2, RL plus m minus 1, where each of these Ri's are consisting of n bits. Okay. So, each of these Ri's are basically this n bit vector. This is corresponding to the transmitted code sequence. So, this R is the received code sequence corresponding to the code word or the code sequence that we have transmitted. Now, we know that a maximum likelihood decoder will try to maximize the likelihood function. So, a maximum likelihood decoder is going to find a path through this trellis that will maximize the path conditional probability. So, it will maximize the likelihood function. Now, we can define the probability of R given V. Now, what is this R? R consists of these L plus M elements, and each of these Ri's are further n bit vector. So, since it is a memoryless channel, we can write this probability of R given V in terms of these Ri's and Vi's like this, and this can be written in terms of the bit likelihood function. So, we can write this in terms of Ri's and Vi's, and this can be written further in terms of the bit metric which is given by this. And what are these probabilities? These probabilities are nothing but these are corresponding to the channel transition probabilities. Now, maximizing this likelihood function is equivalent to maximizing the log of the likelihood function. Why? Because log is a non decreasing function. So, we can equivalently write maximizing this as our objective as maximizing the log of probability of R given V, and this is, we call this as path metric. Now, how do we compute the path metric? Now, go back and look into the expression of probability of R given V. So, if you look at the probability of R given V, it is given by this. So, if we take a log of this, this product term becomes summation. So, we can write basically them as, so we can write our path metric as summation from 0 to L plus M minus 1 log of probability of RL given VL, where L goes from 0 to capital L plus M minus 1, and we are calling this as our branch metric. So, this is our branch metric. Further, the branch metric can be written in terms of bit metric. Now, we know what is the probability of RL given VL. This is given by this expression. So, if we take a log of this, again this product term will become summation. So, what we would get is this. So, you can see we can conveniently write path metric as sum of branch metric, and branch metric we can write as sum of this bit metric. Similarly, we can define a partial path metric for the up to jth branch of a path V as summation of path matrix up to jth branch. So, this is path metric computed from 0 to j minus 1. So, this is what we are defining as partial path metric. Now, what is the maximum likelihood decoding rule for a binary symmetric channel? For a binary symmetric channel, the maximum likelihood decoder is one that decodes receive sequence R into code sequence V such that the Hamming distance between the received code sequence and the transmitted code sequence is minimized. This we have seen in the initial lecture on introduction to convolutional code, that maximum likelihood decoder for a binary symmetric channel will try to minimize the Hamming distance between the received code sequence and the transmitted code sequence. and Viterbi algorithm provides a computationally efficient method of basically just doing that, and it tells us a way to efficiently find a path through this trellis which will maximize the likelihood function. In other words, it will choose a path that will basically maximize the path metric. We will choose a path which will maximize the path metric. So, how does Viterbi decoder works? So, it proceeds through the trellis one time instance at a time in search of the best partial path metric up to that particular time instance. So, you start with time t equal to 1, at that time instance you will try to compute the best path metric at each of the nodes, at each of these states, and this you repeat for next time instance. You do the same thing, you try to find out what is the best path metric for that particular time at that particular state. So, at each level the decoder is going to compute and compare the matrix of all partial path entering that particular state, and it is going to choose the one which has the best partial path metric at that particular time instance. So, the decoder stores the partial path entering each state with the best metric. Note that there are two branches which are converging for time t greater than m, there are two branches which are converging at each state. So, from those two states, from those two branches, it is going to pick up the one branch which gives us the best path metric. So, it will store that best path metric and remove all other path metrics which do not give us the best path metric. So, for time instance L between m and L, there will be total 2m survivors, and during this termination process the number of survivors will diminish until we reach the final state, which all 0 state, where we will be left with only one survival, and then we backtrack to get back our decoded path or decoded code word. So, when we reach the final time instance, which is final state all 0 state, we will be left with only one path, and that is the surviving path is our maximum likelihood decoded path, and then we backtrack to get back what were the code bits and the information bits corresponding to that particular path. So, to summarize basically how does this Viterbi algorithm works. So, let us say starting at time t or L up to m, note up to the memory order there is only one path from the initial state all 0 state to any other state. So, starting at time up to L equal to m in the trellis, we compute the partial path metric for the single path from all 0 state to any particular ms state, and we store the survivor path as well as the metric value for that particular state. Next, we increase the time by one instance, and now we compute the partial path metric for all the paths for at that time instance which are entering that particular state, and we compare the partial path metric and choose the one which gives us the best path metric, and we ignore other paths. So, at next time instance we are going to store the survivor path, which is the one which has the best metric, and we will also store what its metric value is. And how do you compute the partial metric at time L plus 1, given that you know the path metric at time L? So, what we do is we add to the path metric of time L, we add the branch metric value to whatever is the partial path metric at that particular state, and that is how we compute the the path metric at time L plus 1. Now, this will be clear when we illustrate this with an example immediately after this. And we repeat this process until we reach the end of the trellis diagram. So, let us come to an example to show how we compute the partial path metric, how do we choose the best surviving path, how do we eliminate other paths which do not give us the best path metric. Okay. So, let us take an example of a rate 1/2 code which has memory 2. This is the encoder of a rate 1/2 code. We are given that number of information bits were 5. Now, since its memory is 2, we require 2 bits to bring it back to all 0 state. So, total basically we are transmitting 5 information bits plus 2 tail bits. So, total 7 bits, and since it is a rate 1/2 code, so 7 bits will result in 14 coded bits. So, this is basically the receive sequence corresponding to those 14 bits that we transmitted. This is the receive sequence over the binary symmetric channel, and the question that we have to answer is, given this receive sequence, we need to find out what is the transmitted code word or what is the transmitted information sequence. So, how do we proceed? The first step is we will draw the state diagram of this convolutional encoder and we will draw the trellis diagram of this convolutional encoder. So, what I have here is I have drawn the trellis diagram of this rate 1/2 convolutional encoder. Please note, initially we are starting with all 0 state. So, this time instance 1, 2, 3, 4, 5. These were our information bits. Now, what happened after this? We are terminating the convolutional code to all 0 state. So, number of states reduces by half at each time instance. So, from here from 4 it becomes 2 and from here it becomes 1 state. So, you can see basically we are transmitting 5 information bits and 2 tail bits. And what I have labeled here is I have at each branch I have labeled what is the code word correspond to this transition. So, what is the first step? We will first try to compute the partial path metric up to time t equal to 2. Why time t up to 2? Because the memory order of this convolutional code was 2. So, from all 0 state up to time instance 2, there is a single path from all 0 state to any particular state. So, for example, if you want to reach state 0 1, we can reach it from first we will go to 0 0 state to 1 0 state, and from 1 0 we will go to 0 1 state. Okay. Now, how do we compute these path metric? So, let us go back and see what our first 2 receive sequence were. It was 0 1 and 1 1. So, we had received here 0 1 and 1 1. Now, remember, for binary symmetric channel, the maximum likelihood decoder is trying to find the Hamming distance between the receive sequence and the code sequence, and it will try to choose a path which will minimize the Hamming distance between the R receive sequence and code word V. So, let us look at this path from 0 0 to 0 0. What should have been the code word 0 0? We have received 0 1. So, what is the path metric corresponding to this? That is 1. So, this is the path metric. Now, look at here, code sequence is 1 1, this is 0 1. So, path metric is differing in Hamming distance 1. So, that is my path metric here. Now, what is the path metric here? This is equal to the path metric, partial path metric at this time plus branch metric corresponding to this. So, this is 1 0 and what we received was 1 1. So, what is the Hamming distance between 1 1 and 1 0? That is 1. So, 1 plus 1, so 2. So, this will have a path metric of 2. Similarly, this, what is the path metric at this instance? So, note the branch metric is for this branch is 0, because code sequence is 1 1 and receive sequence is 1 1. So, Hamming distance is 0. And what was the partial path metric? The partial path metric here was 1 plus 1 and the branch metric here is 0. So, 1 plus 0, that is 1. Similarly, we can find out what is the partial path metric here. This is going to be partial path metric here plus the branch metric of this. And what is the branch metric of this? This is 0 1 and receive sequence is 1 1. So, it is differing in the first bit location. So, 1 plus 1, that is 2. And similarly, here the partial path metric is 1, the branch metric in this case is 2. So, 1 plus 2, so partial path metric here is 3. And this is what I have also illustrated here. Our receive sequence was 0 1 and basically these are the Hamming distance between core sequence and the receive sequence. Now, once we know what are the path metric here at this time instance, the next step, what do? We need to find the path metric here. Now, how do you find the path metric here? Now, note here we have two branches which are entering the state. One is this, other is this, right. So, how do we compute the partial path metric here? This we compute by adding to the partial path metric of this state plus the branch metric of this branch, or the path metric at this state plus the branch metric corresponding to this transition. So, we are going to choose which one of these two is a better, gives us a better path metric, and then we are going to choose that path as our surviving path, and we are going to delete the path which does not give us a best metric, and we will also store what is the best path metric corresponding to that particular transition. So, we are looking at this time instance, this trellis section, we are looking here. So, what was the receive sequence? Here it was 1 0. So, what is the branch metric corresponding to this transition? This transition. This is 0 1, this is 1 0. So, Hamming distance in this case is 2. And what was the Hamming distance here? Path metric was 2. So, 2 plus 2, this would give me partial path metric of 4. Now, let us compute the path metric of this. Here the partial path metric was 1 and this was 1 0, 1 0 and 1 0, the Hamming distance is 0. So, corresponding to this path metric is 1. Now, which one is a better path metric, 1 or a 4? This one is a better path metric. Why? Because Hamming distance here is less, it is 1, whereas for corresponding to this path it is 4. So, what we are going to do? We are going to delete this path and we are going to keep this path. Not only we are going to keep this path, we are also going to keep the corresponding path metric, which is 1. Similarly, we will do the same step for other nodes. Let us just take this example, this node 0 1. So, one path metric we will get by adding to the path metric of this, partial path metric of this, which is 1, and 0 1 and 1 0, which is Hamming distance of 2. So, 1 plus 2, this path is giving me a partial path metric of 3. What about this path? This is 2 and this is 1 0, 1 0 1 0, Hamming distance is 0. So, 2 plus 0, that will give me partial path metric of 2. Now, clearly this is not the best path metric. So, I will keep this surviving branch and corresponding path metric, which is basically given by 2. So, at each node I am going to find out partial path metric corresponding to all the branches that terminate at that particular state, and I am going to keep the same, I am going to keep the one which gives me the best path metric. I am going to keep track of what is the path metric value and also keep track of the surviving path. So, this step will be repeated. The same thing I do here. Now, let us take an example here of this particular node. Now, how do we compute the path metric here, the partial path metric here? This is the partial path metric here will be either partial path metric here plus this branch metric, which is 1 0 and 1 0. So, this is branch metric here is 0. So, 3 plus 0 is 3. Now, let us look at this. The partial path metric here is 1 and this is 0 1. So, 0 1 and 1 0. So, this Hamming distance is 2. 1 plus 2 is 3. So, note here both the paths here have the same path metric. So, there is a tie. So, what do I do when there is a tie? So, in this case both the paths are equally likely. So, I can just pick any one of them. So, this process is going to be repeated. So, I will continue with this process. So, again I repeat, at each time instance what I am doing is I am trying to compute the partial path metric at each of these states. And how do I compute the partial path metric at each of these states? This is the partial path metric at previous time instance plus the branch metric corresponding to the transition which will bring you to that particular state. And when you have multiple branches converging at particular state, you need to pick the branch which will give you the best path metric. That will be your surviving path and you need to keep track of the metric value as well. So, we continue this step until we come to the end. So, as we know, after 5 bits, because tail bits are coming, so number of states are getting reduced. So, from 4 the number of states became 2 here, and then you have number of states basically 1. So, once you come to this point, then there will be only one surviving path. Okay. So, once you have only one surviving path, then what you need to do is you just need to backtrack to find out what is the transmitted code word. So, you can see here when we reach this all zeros final state, there is only one surviving path, and that path, if we track back, it is this path, this path, this path, this path, this path, this path, this path. So, you can see there is one survival path basically that you will get, and this is my decoded code sequence. So, corresponding to this receive sequence, my decoded code sequence is 0 0, 1 1, 1 0, 1 0, 0 0, 0 1, 1 1. Okay. And this is basically shown here. So, this is my backtrack path and this is my estimated code sequence. So, this is how basically we decode a convolutional code using Viterbi algorithm. Thank you.